little bit different than your traditional heap overflow where you get to control all 4 bytes and you get to control exactly where it goes. In this case, you get to control where it goes, but only part of the bytes. And there's a little example of this is, okay, so typically UCR descriptor will point into unused memory, and our overflow can overflow the UCR descriptor. And we go ahead and create, and we point it back to some function pointer that we know on the stack relative, or heap, or wherever it might be. So this is the target data that we want to overwrite with part of that header. Then we cause a bunch of allocations, and when the new segment would be allocated, that structure gets written there. And so that's just 2 examples. There were a couple others that we worked on, but 2 examples, kind of different way of thinking about it. You know, you're writing more known data rather than controlled data. You're worrying about overwriting only parts of function pointers rather than full function pointers. And also, you know, a lot of people hadn't been attacking the more higher level data structures rather than just the individual block structures. So low frag heap is, like I said, it replaces the look-aside lists, and it's very similar. It uses 128 buckets, just like the low frag heap did, and those buckets are each for different sized allocations. And it's automatically turned on after a certain number of allocations. The heap manager keeps a count of how many times a certain block had been allocated. And so we're kind of short on time, so I'm not going to spend a lot of time on this here, but this is actually the entire kind of data structure association for the low frag heap. And the low frag heap, it's important to remember, is allocated within the standard heap. So this is all sitting in a virtual alloc chunk that's done by the main heap manager, meaning essentially that all these data structures are accessible not only from an overflow into something on the low frag heap, but in an overflow into any sort of heap buffer. The important thing to note here, I guess, would be the 128 buckets. They're defined up at the top here, on the top left, those buckets right there. That defines the properties of each of the buckets. And then there's an array of those buckets for each CPU that are called the heap local segments. And then those segments contain subsegments, which are actually the containers of the blocks. And so those are metadata headers that top of the user data header, which actually do contain the blocks. And the nice thing about the low frag heap is that if you look at the way that this is laid out, it can all be accessed through a couple of indexes into arrays, which is why the lookups are so quick. And so I have one example here, and then I think I'm going to get kicked out. But the low frag heap block zone, if you look right here, is in the top right-hand corner. So this is the top-level structure that's going to be on top of a series of blocks of the low frag heap. And the attack is, there's a free pointer in the block zone, and the free pointer says where the next heap subsegment allocation will occur, kind of similar to the last attack. And you can actually control some of the fields here. Oh, actually, there's down on the right, that's the structure we're talking about. So the, right, is it free? Yeah, okay. So you can control a couple of those fields, and those will actually modify what the new header. So you actually have even more control than just a blind static structure. You have control of some of the new fields that are going to be in that structure. The assessment of this one, though, is that this is a multi-stage attack. It will involve kind of a series of allocations, and then your overflow, and then another series of allocations similar to the last one. And without something like JavaScript or something with high degree of control, a lot of these scenarios are going to be difficult. It's going to be very application. How many network connections can I make? How much activity is on this machine? Am I going to be able to control the amount of allocations the way that I need to? So effectively, at the end of the day, I think that a lot of times it's going to be easier to attack the application-based data that's in the heap because of the degree of complexity it takes to actually have the precise control for some of these attacks on the metadata. And then finally, I'm just going to close. There's a chart that kind of summarizes the current feature sets of different operating systems and their memory hardening. And just want to end with, OS vendors have a unique opportunity. So if you guys are contributing to FreeBSD, OpenBSD, any open source operating system, maybe you're an Apple employee, I really hope these messages reverberate through those societies because, I think we can do a lot by adding mitigation technology to the operating systems and really reduce the effectiveness of reliable. But in the end, I mean, they don't solve the problem. Software has to be written securely. We have to get rid of those bugs anyways, but they do provide like that stopgap, in that time frame when, that 0 days out there and people don't want to get owned. So it's kind of that extra layer of protection. And that's it. So any questions? Yes?
When you talk about the image base being redlined only once per boot,
I'm sorry. Can you?
when you're talking about the image base being only redlined once,
Yes.
now am I to assume that when kernel 32 gets loaded up the first time, that only gets redlined once?
Correct.
Okay, so if you got 3 shots from service restart, couldn't you pull the address from kernel 32 out, and then use your second shot to really check the stuff?
Well, I mean, if you were able to leak an address within kernel 32, sure. Yeah, but I mean, and again, this is going to be remote. So yeah, if you were able to acquire any address within kernel 32, then yeah, the next time it booted, it would be somewhere within that range, Correct. Mm-hmm. Oh, absolutely. That's exactly what the information leakage approach is all about. It's, use one of those crashes as if you have to, or try not to crash it. But if you can get an address the first time, when it reboots, the libraries will be in the same spot. Not at this time, although I am advocating that internally. We just, at this time, I guess it hasn't been a widespread, there haven't been too many widespread remote attacks on kernel space, and so for Vista, it was kind of a push to get this in here. So we might see that for Longhorn, but it's something that we're looking to for sure. Yes? Well, actually, there's plenty of opportunity to increase the entropy. At this time, in Vista, the first rollout, since this is kind of new technology, the entropy is identical across both architectures, although you will see that change in the future. Right now, it's the same. I'm really hoping we can get that change for Longhorn. There's, there's definitely about 24 more bits that you could play with there. Any other questions? I'd just like to note there's a new alias I created at Microsoft, actually. So if anybody's interested in mitigation technologies or does their own analysis of ASLR on Vista or whatever it might be, and you have some dialogue that you would like to have, maybe some ideas, or even maybe you're implementing your own things, please feel free to email us there. It's just me and 1 or 2 other guys that are kind of the engineers on these projects, and just kind of wouldn't mind some community feedback. If you think we suck, if we think there's ways we could optimize the amount of entropy, please contact us. And with that, if there's no more questions, thank you very much for coming. Yeah.
I'm actually third or fourth one.
Okay.
Well, that and also
Oh, cool. What was your name? Justin. Cool. I'm sure I'll see you in the office then, because right down that aisle. Hey, man. Hey, thanks. Kind of like, I felt like I had to go twice the speed I usually would, because there's just not much time for this.